So, hallo. Danke, dass ihr alle gekommen seid zur NoSQL User Group. Ein paar von euch kenne ich sogar, aber einige noch nicht. Das ist schön, dass immer auch neue Leute kommen, die vielleicht noch nie hier waren. Heute trägt der Tobias was vor zum Thema Cockroach oder CockroachDB, heißt es, glaube ich. Ne?
Beides.
Beides?
Austauschbar.
Habe ich selber noch nie von gehört. Es soll aber angeblich auf dem Spanner oder dem F1 von Google basieren oder auf demselben Konzept basieren, ist aber eine Open-Source-Implementierung, die sozusagen von jedem benutzt werden kann und nicht nur von Google intern. Was erstmal aus meiner Sicht sehr vielversprechend klingt und ich bin also sehr gespannt, was dahinter steckt. Wie gesagt, ich habe nie was davon gehört, ich weiß nicht, wie es euch geht. Ich würde einfach mal das Wort an Tobias übergeben und ja, wie ist es mit der zeitlichen Vorstellung bei dir? Also,
ich würde schauen, eine Stunde, länger will ich eigentlich nicht machen.
Okay, gut.
Also,
wir haben jetzt keinen anderen Vortrag heute, das heißt, du bist der Einzige, das heißt, du kannst eigentlich aus meiner Sicht so lange machen, wie du willst.
Ja, ich versuche euch nicht zu langweilen und ja, ich werde auch mal unterwegs in die Gesichter schauen, wenn es irgendwie so aussieht, dann werde ich ein paar Mal Enter drücken. Nächste Frage, für mich ist es bequem, das irgendwie in Englisch zu machen, weil die ganzen Namen üblicherweise Englisch sind und es möglich wäre, dass ich mich auf Deutsch verhedder. Einwände? Jemand, der es unbedingt auf Deutsch haben will? Nee? Okay. Ich versuche langsam zu sprechen. Kann manchmal schief gehen, aber sei es drum. Okay, then thank you all for coming. I'm here today to talk about Cockroach or CockroachDB. We actually prefer to call it Cockroach because Cockroach is a nasty thing and we really want this nasty aspect to stick with you because we want you to remember it. It's kind of a neurological programming trick. But on top of that, the database that we're building actually has a couple of things in common with cockroaches. If you think of cockroaches, well, you probably think of someone who isn't yours kitchen with a bunch of cockroaches inside. That person will try to get rid of them, maybe run around, squash them, but that's not really how you get rid of cockroaches. You need a professional. Cockroaches are really resilient, really hard to get rid of, really hard to kill, and our database also aims to be really hard to kill. Another thing about cockroaches is if you have a small group of them in someone else's kitchen, not yours, then they will usually multiply kind of autonomously. You don't have to tell them what to do, where to go. They will figure it out on their own. Said in technical terms, deploying new cockroaches to your kitchen, it's almost doing it itself. And our database too will try to make it as easy as possible to actually scale out and will not have you burdened with figuring out which data to put where and maybe have sharding. We don't want any of this. We want it to be very simple. So that's where the name Cockroach comes from. Maybe another reason why it's called Cockroach. A lot of the people that actually came up with this thing, they're in New York, a lot of cockroaches. So maybe an inspiration was found there. Okay, so before I get into the details about our design, let me actually just talk a little bit about the history, because I think one thing that we really need to do today, because I'm presenting on a new database that we're writing, and there's already more than I know out there. Really, one thing that we have to do is motivate why are we building another one? What kind of use case are we filling here? State of play that we have so far, I mean, SQL, everyone knows it. It's been around for maybe 4 decades. You think of large monolithic servers, very consistent transactions, very nice unless you don't have more data than you can put on this machine or more users than this machine can handle. You need to scale. It's kind of nasty and you cannot really scale horizontal that well. You cannot really replicate everything that well. There's kind of techniques that try to make it work, but everyone who's done that will probably agree it's not the most fun thing to do. Then a bit more than a decade ago, NoSQL came along, basically out of the need to be able to scale more easily. And basically what happens is that you kind of went the opposite direction from traditional RDBMSs, where before you had transactions and strong consistency. Now you said, well, and I really have to scale. I really want to be able to service clients even if my network is about to die. I'm just going to, ditch this for now. Be eventually consistent. So if parts of my database diverge from each other, at some point in time, they'll just kind of meet each other again and update to a state that's shared. And something like joins and more relational features are usually very difficult in those systems. And then maybe about 2 years ago, something happened which we think is very worthwhile pursuing, which is that those two worlds kind of merged again. So people took a step back and thought, well, most of our data is actually relational. Probably we went a bit overboard with this, tossing away transactions and consistency. Let's take a step back and try to build systems which both are available and really nicely scalable, but also retain some of the consistency that we had in our original database world before we went NoSQL. Okay, so basically have cake and eat it too. Of course, there's always something that you pay, but let's first trace this history about going from SQL to NoSQL and then to NewSQL at Google. In 2004, they came up with Bigtable, which is a key value store. And it's basically what you picture if you think NoSQL. It doesn't have transactions. It has eventual consistency instead. It's very scalable, super available. I mean, it's built by Google. And one of the guys on our team actually worked at Google in 2002 before they had Bigtable, and he worked on AdWords, which, as you know, is a huge product for them. And they were actually running it on MySQL. So they had, in the beginning, a couple of shards, then it grew to maybe 22 shards. I think at the end they had 30 shards. And it must have been pretty painful because at some point they had their thing all sharded out and they already had a couple of hacks in place. And then eBay came along and suddenly they had one customer that they couldn't fit on any of their individual shards. So they had to find a solution for this, and it was really a pain. So I'm pretty sure everyone at Google was pretty happy when they got Bigtable, and a lot of the products actually migrated there. But then over the next years, people began to realize that they kind of needed to be consistent at least some of the time. And the infrastructure guys at Google got more and more complaints about Bigtable not having consistency, and that caused kind of data integrity issues, kind of added bloat code to the app, which now had to handle this kind of thing, which is tricky and very error prone. And so Google did what a company would do if they have a lot of very good engineers and they have a problem that they need to solve, and they just built it on top of what they had. And that is how they got Megastore, which is basically an extra layer of complexity that they put on top of Bigtable, which added transactions. And well, as you can picture, because Bigtable was not made to have this feature, it was very complex, and the worst thing was very slow. So I cannot tell you exactly how slow it is, but the people who worked at Google, who are now working on CockroachDB, say it was very slow. But still, a lot of applications migrated to Megastore because it made their code much simpler, and performance, you kind of have to deal with it. And everything else that came after 2006 at Google mostly preferred to use Megastore over Bigtable. And that is not for the reason that Megastore was so fast, but it was because it was consistent. You could actually write the code on it without being too complex. And well, you can see this is kind of a workaround solution. And then finally in 2012, they had a pretty seminal paper in which they described Spanner with F1 on top of it. But today I will not talk about F1 really. So they had Spanner, which is a globally distributed, linearizable key value store, which means that basically this was a key value store that logically just behaved as if it were on a single database. So it really had linearizable transactions, which is the best thing you can ask for. And they put back relations into it. So Spanner itself is really just a key value store, but then because you have those strong consistency properties, you can actually implement something like SQL on top of it. So this is what Google did. So you can really see that Google itself kind of had a learning experience there. And in the Spanner paper, they put it like this. They say, we believe it is better to have application programmers deal with performance problems due to the overuse of transactions as bottlenecks arise, rather than always coding around the lack of transactions. So Google figured, well, if it's slow, then maybe we should look at this specific part. But baseline is we do want to have transactions in our database, and that's why we built Spanner. And maybe actually I should go back and say a little bit about consistency, because it is very central with Cockroach. And I will just give like a super short definition that's not very precise. And I will define two things, which is, well, I should go back more. It says here fully linearizable. And this is small, right? This is only so that the name means something. OK, so I will define linearizable. And before I do this,
maybe the next one. Yeah.
Try one of those.
Thank you. Oh, yeah. Yeah. Nice little drawing lesson. OK, so linearizable and serializable. So I'm assuming that some of you could just write down the whole definition of those two things from Wikipedia. But in case someone is not able to, I don't want to talk about those things all the time and not have kind of explain what it is. So serializable is the one that we need most in this talk. And serializable basically means if you have your abstract database sitting here somewhere, and this could really contain a lot of different nodes, run in different data centers, whatever. And you have down here a bunch of clients, and all of those run transactions concurrently. So all those transactions will overlap. Then the state of the database as a whole will change. And for serializable, what that means, if the consistency level is serializable, that means if I take, say, 10 transactions and I run them at the same time, and then I compare the state of the database before they all run and after they all have finished running, then I can alternatively start from my initial state and I can choose the transactions in some order, which I don't know in the head, but there's some order that I can choose. And if I run one of the transactions after the other without them overlapping in time, then I will get the same final state. So from the viewpoint of a transaction, each transaction is alone on the database while it runs. Even though in practice, of course, a database will run more than one transaction at a time, which is completely reasonable because most of the time they won't even intersect. And if they do, there's concurrency control methods that allow you to still do this. But logically, you want something to be serializable, and that means that each transaction will look like it's alone. So transactions, how do I say this? Logically, only one transaction at a time. And then linearizability can be hand-wavily defined as meaning kind of the same thing, but now you have a reference to absolute time. So linearizability is if you actually get to specify the order in which the transactions happen. Okay, so serializable doesn't tell you in which order the database will internally, in its logical state, have applied the transactions. But with linearizability, there's actually a reference to an external clock, so to an absolute ordering. So I will just very hand-wavily write serializable plus absolute time. I could also write ordered with respect to absolute time, whatever. We won't need it that much, but I definitely want to know that you have a picture. Okay? So now I get to jump ahead 2 slides to where I was. Okay, so now that I have the definitions down, I can actually start talking about Cockroach. And the first thing I should do is show you this screenshot from the GitHub project contributors page. And I blurred everyone because there's one person that's more important than the others if we face it. That's Spencer Kimball. He's a guy who was working at Google for more than 10 years and actually was part of this AdWords team that had the sharded MySQL nightmare. And so he basically worked on infrastructure there, thought about databases for about 20 years. And he wrote the initial design documents for Cockroach and has basically assembled this team of mostly ex-Googlers, and I'm also here, that are now mostly based in New York and working at Square. And they ended up there because they all left Google with Spencer, had a startup. That startup was bought, and now they all sit in New York and work on this in their free time. Except for Spencer, I think Square has allowed them to just work on this all the time. Okay, so that's the team. And you can also see that Spencer has punched in the lion's share of the code, and everyone else is kind of trailing behind. And another fun fact, Spencer and Peter Mattis right here, they wrote GIMP. So you've probably used their code at some point. Okay, so let's talk about the design principles of CockroachDB. So those 3 points right there, they're kind of what we think is important for a database that people would use in 2014 for most of the general purposes. And that is, of course, scalability, high availability, but also transactionality. I mean, I've hinted at it enough now that we think this is something that's going to be more important in the near future after this kind of eventual consistency craze kind of ebbs down. Because most applications really need either 2 of those, but mostly, at least over time, as your application matures, you're going to want all the 3. And now I'm going to just briefly talk about each of these legs, but I mean, scalability is pretty, probably don't have to say much. Data is king, you want to store everything. Maybe today you don't exceed your data in what you can store on a single node, but you definitely want to be able to not be locked into one particular system that doesn't scale out. If you have to vertically scale, a lot of companies these days have that problem because they're still stuck on their old stack, so they have a hard time getting out of there. It costs a lot of money. Sharding is complex and limiting. I don't have to say anything. And ideally, what you want to have is on-the-fly horizontal scaling. So you add new hardware, new virtual machines to the cluster. You have some amount of configuration, but not too much. And then ideally, even the data doesn't have to be moved there manually. Ideally, the system has enough self-awareness to just kind of take part of the load, a part of the data, and move it there. And the app shouldn't really know what kind of database it's dealing with. The app, as with sharding, you often have the problem that the app has to know which shard to address for which operation. And so a lot of your database infrastructure leaks into your app. If you have to change anything, it's going to be very, very complex. I could tell interesting stories that Spencer had at AdWords, but maybe I'll keep that for the question section or a beer after. It's really complex, and your app shouldn't really know. And well, third point, simple homogeneous infrastructure and deploy. I mean, in a perfect world, everything looks the same. An example where everything does not look the same is Spanner, because Spanner has a very, very complex system. I think that's initially why Jan read the paper and said, well, it would be nice if we had this, but no one's ever going to have this outside of Google. Because Spanner requires Colossus, which is their distributed file system, which internally has masters and slaves. And then they have a choppy locking service, which is another service that basically keeps track of which parts of the system they've locked, which also has to be distributed, of course. And then they have GPS receivers and atomic clocks in each data center or close to each computer. So it's a nightmare, and you have this zoo of different things. And well, I will not want to deploy this, and I don't think many people outside of Google can actually pull this off. So we want this to be simpler. OK, and then second leg, availability, is a bit harder to talk about because the terminology comes from a time when people didn't really have scalable systems or distributed systems. It's kind of 1970-ish. But the CAP theorem, which I have to talk about, is more recent. It's something that was introduced by Eric Brewer, who's a computer scientist in the USA. And basically, what the CAP theorem is talking about is about the options that you have for your database behavior in the face of network partitions. And I'm going to try to write another great picture down here, which may well fail, but let's see. So the C, A, and P in CAP stand for consistency, availability, and partition tolerance. But really what it means is in the face of network partition. So if you have a network partition, what is your app going to do, your database going to do? You can either be consistent or you can be available. You cannot be both. And before I try to define available and consistent in long wordy terms, I will just draw a picture. Learned in university, that's usually the best way to go. So those three are my data centers. I'm not even going to name them. And the CAP theorem talks about what happens in the face of a network partition. So let's partition the network. A very simple network partition is one in which one of the data centers gets cut off from the rest. So now this guy cannot talk to either of those two because maybe some router, whatever, failed. Something is weird. We don't know why, but they cannot talk. And those two guys, on the other hand, they can talk. And of course, down here, we have a bunch of clients who want to do some stuff with the database because people are using it all the time. It's very popular. And we don't want it to go down. OK? So now the CAP theorem says if the situation happens, then our system has to choose between consistent and available. And this is very nicely illustrated by having one client who wants to write maybe here. So if I accept this write, if I let this client write here, then maybe at the same time some other client is writing into this part of the database. And maybe those two writes are conflicting. But the two parts of the database are separated, so they will never be able to know, at least not in this situation. So what you've done at this very point, if you accept this write down here, is you have stopped being consistent because you have conflicting data here. And once the network partition goes down, you will kind of have to do some merging, which will lose some semantics of the data that was written. Or even before that, well, if this client writes an X here, and then another guy that doesn't know it's already written in this part of the database will try to read the same key here, maybe we'll get a different or no response. Even then, you've already lost any type of consistency. And what you need to do in order to be consistent is, at least in all common cases, because we're going to be using consensus protocols, is to kind of disallow the minority component on the network split side to serve requests. So if we are choosing to be consistent instead of available, this guy here would not be able to do anything until the partition is resolved and until the guy has come up to speed. So this is basically the CAP theorem. Okay, and in typical big table, NoSQL in 2005, or maybe not too much later, would be to just serve whatever you have, and then when the network comes back up, you just kind of match it together until it looks the same on every place. Okay? So yeah, I've already explained this, I think. Available in the sense of the CAP theorem means that every part of your database that a client can reach will actually answer with the response to the work that is being requested. So in this situation here, where this minority component of the distributed database stops responding, you have failed to be available in the sense of the CAP theorem. But of course, you can still be fairly highly available because the a majority component of your cluster will still work as expected. So for Cockroach, the way it would work, a data center goes down, loses connectivity, usually, unless you, yeah?
What happens if a client is only available to see the one data center?
You mean if a client has connection issues? It doesn't matter. So the consensus stuff happens inside of the Cockroach network. It doesn't matter what the client does.
If the network connection is broken down?
So wait. So
applications only available, all clients only available to the single data center.
Oh, so you're saying if the network partition is like this?
Yeah.
Well, then the client cannot talk to it. I mean, because...
So the clients will all fail?
Yeah, because if your client can only talk to one data center and that data center cannot talk to anyone else, then you're gone. This is something you really need to have. I mean, assuming you have like 3 data centers, which are in different places, this is something that's fairly unlikely. I think if you start with data centers that have 3 nines of availability, then this kind of situation typically would happen with like 4 or 5 nines and a 6. So this is kind of stuff we can crunch later. But of course, yeah, this is absolutely true. There are situations in which you will stop responding because otherwise you would be available in the sense of cap and then you cannot be consistent. But the point that I would make is that you can be highly available by separating your data centers, and usually you need no more than 3. You can do 5 or 7, but there's a limit in how useful this is. Usually will give you very high availability. And this is what happens with Spanner or anything that uses Paxos, for instance. Usually those things all are consensus-based, which means that you need a majority to agree on something that's going to happen. And any system that works in this way will fail if you cannot reach the majority. And that's really the hard line that you cannot cross. Yes, and so ideally your app should notice. Of course, if you cannot talk to anyone who's available, then you lose. But usually your client will have, or your app will have a couple of entry points into the system. And if one of them goes down, you just try the next one because your database is consistent, or at least tries to be. It's easy to get wrong, but should be consistent. Then you will be able to carry out the work on another server. The only thing that might happen is that you have to choose a data center which is not closest to you. So maybe your latency goes up. And you're not going to like this, but it won't kill you. Okay. In an ideal world, something like this happening shouldn't even be a reason to ring up the NetOps guy at 3 in the morning. This should be something that the system handles on its own. Next morning, of course, you have to look into what went wrong, but maybe it's just AWS killing a switch, and then there's nothing really you can do. Yeah, so we're trying to be CP consistent, partition tolerant, and we're trying to do this in a way that's as available as possible, which I will call highly available. And doing this is really difficult. It's also part of why Spanner is so complicated, because it's really difficult to get this right. And this is basically all that we do all day, is to try to get this right. And we're not trying to tack any fancy features on it at the moment. We're really just trying to nail this part completely, to test it until we cannot think of anything else to test. OK, transactionality, third, sorry. Yeah, we want all or nothing semantics, and we really want transactions that are what you think transactions are. So the being ACID compliant, which means atomic, consistent, isolated, and durated, I guess, is also a durable. But if you want to put into an adverb, then that's why I had to do this kind of yoga. Yeah. Persistent maybe, but then it's another word. Anyways, that's also a term that comes from traditional databases, and it's also, fulfilling this is also depending on what you offer. If I give you a key value store that doesn't even have a notion of transaction, then all that it means to be consistent is that I'm atomic, more or less, so there's nothing really to fulfill. But really, we really have a full model of transactions. You can run complete functions in transactions, read values, make actions depend on values. Right now, on the lower level, you can basically run any function in a transactional context. So it's very powerful, and we have full ACID compliance for this. And what that gives you in the end is you have a really simple programming model, because in your applications, you can make use of all those transactional features. And so your code will look very intuitive, and it doesn't have any weird nooks and crannies. You don't have to think about weird anomalies that could happen with lower isolation levels. You will never have to remember what read committed means or what kind of things can happen with read committed. I honestly don't know right now. And also having this powerful notion of transactions gives us a lot of things that we can add on. similar to what Google did. I mentioned earlier that a spanner is a key value store, but they actually implemented F1 on top of it, which gives you SQL more or less, with indexes, full text indexes, I think, and joins and whatever. And that only is possible because you actually can bundle up operations and you have strong guarantees about what's going to happen. What you do not have with this model is half-finished operations. And I'm sure some people can sing a song about how this can creep up on you. Maybe you're running something in your app that usually never fails, but then someone introduces a bug in the middle, so now this fails 10,000 times. Now you're going to write a script that kind of cleans this up. True story. Yeah, so you definitely want to be able to do things completely or not at all. And another whole kind of notion that kind of drifts around with transactions is that they automatically have to be slow. I mean, if you look at Megastore, it's definitely true, but that's because Megastore was not built with transactions in mind. It was built on top of Bigtable, which was not built for transactions. So I hope that by showing you the details about how we implement our transactions, you can actually see that it should be very fast. Of course, there could always be use cases in which you see a lot of restarts, but at the very least, if you don't use the transactions, they have very little overhead and they will not, ruin it for everyone. What you do have, however, since Robert is here, if we compare what we're doing to Cassandra, what you have in any case, if you are going to be consistent, is you always have consensus latency. So before anything goes into your system, you always have to make sure that you talk to the majority of the nodes. So that's something that if you just go for eventual consistency, completely like Bigtable, you just have to write it somewhere because no one guarantees to you where it goes after. So there's no guarantee given, so it's very easy to write stuff. And for us, we actually have to make sure it lands on all the servers, and we have to get this completely right, which is also very difficult. But that would be another talk. But yeah, it's very difficult. So now that I've talked a lot, let's actually see what it would look like. So the stuff that's inside the distributed cloud infrastructure is actually more the physical infrastructure. So each Cockroach node right here would correspond to an actual machine. So something that you deploy to AWS or maybe something you have in your basement, depending on the type of company that you're at. And you can have a lot of those nodes. It's really easy to add them. In this example, I've hinted at the fact that there are 100, but you could have thousands. I think theoretically, we can do up to 4 exabytes of data, but I'm not sure how many zeros this is, but it's a lot. So this is really designed to be something that Google could use if they didn't already have Spanner. Okay, so each physical logical machine is one of those bars here. Each machine will have a bunch of hard drives, so usually SSDs, but you could use an HDD, but you don't want to. And what we use on the very low level, let's go from the inside out. What we use on the very low level to actually store data. So remember, Cockroach is a key value store. So what you're storing is a key, so bytes, a bytes array, and an associated value, so also a byte array. And the byte arrays are sorted lexicographically. Okay, so you have a sorted key value store. And on the very low level, at least at some point, we have to store them on the physical machine somehow. And we're doing this with RocksDB. And RocksDB, just very briefly, is a fork of LevelDB. LevelDB is something that Google built as a high-performance key value store. And Facebook then wanted to use LevelDB, and they looked at it and they said, well, this is not good enough. We're going to fork this and make it better. And specifically what they made better is they improved the performance specifically for cases in which the data that you're storing does not fit into your memory. So LevelDB was blazing fast as long as you didn't exceed your RAM, and then suddenly, it was not that great anymore. So they built RocksDB. Great guys. I think we have the storage engine part nailed down with them. We don't do much with that. We're just leaving it to them to be great. But yeah, basically this is a log-structured merge tree, so same kind of data structure Cassandra uses and a bunch of others. So that's how some keys are stored inside of a single machine. And then you have all those single machines, and they form the cluster. But as a client, of course, you don't want to know about the cluster. All that you want is a single monolithic key value store, and that's the first abstraction that we're building. And I should add as a disclaimer, well, the reason why I'm not wearing a CockroachDB shirt tonight is because, well, it's before beta, so you cannot actually deploy this. It exists. It has like a lot of code and a lot of tests, but we're building it from the inside out. And for beta, we're actually publishing the first working version that people would want to use, which ends at the distributed monolithic key value store. So first thing we're going to build is a highly scalable monolithic key value store. And the way it's going to work is you have a client, and it can just connect to any of the IPs that are in your cluster, and it will just work, and you can access everything. Okay, so we're completely abstractify away all the underlying structure. Then more aspirational, but very realistic next step is a structured data API. This will be the first step towards what Google did with the F1, with Spanner, with SQL. We want to have an API that basically talks about rows of a table and tables and indexes and joins maybe. And then once we have this, adding SQL on top is the next thing that's aspirational. And I'm pretty sure to get full SQL will probably be hard. I think we're aiming for whatever Google is doing with F1 because they probably tested the boundary pretty far. But even that will probably take a couple of years. And you probably shouldn't be banking for subselects at this point, but basic SQL should work. Okay, so this is the comfortable situation that we're in. Is that as far as theory goes, Google has blazed the path for a lot of things, so we know this is possible. If you have a good key value store, you can actually do this sort of thing. But internally, we're doing a lot of things very different from Spanner, which you can see from the fact that we don't require atomic clocks, which we couldn't afford, so we couldn't even do that. Okay, but let's look even closer, so maybe to get the transition right. So I've pointed at the individual machines here, and so now in the next slide, we're zooming in closer to 4 machines, and I will tell you kind of how we bundle up the data that we store. So remember, in each machine, let's say, well, here's a picture of one hard drive, one RocksDB instance, that is, which sits inside of one machine. We have keys which are sorted. And in total, for illustration purposes, I have here the key range from A to Z, so the alphabet. And for instance, if I added the key ABC, then it would go into this key range here, because it's between A and I. So we bundle up packets, key ranges, into smaller logical units. And we do this because we want to be able to shift them around between machines as we need it. So Cockroach is aiming to have each of those ranges here in any of the servers be of size between 30 and 60 megabytes, because that is a good size in that it contains actual honest bunch of data, and you can move it around between machines rather easily because it's not that great and your bandwidth is super high. Okay, and because we are consistent, we actually have to replicate this data. So each range here, which I've color-coded, is present on 3 of the servers. So you see here A to I is on the first 3, and well, all the other ranges you find on exactly 3 of the servers. And with that logical cutting, you can basically shift things around as you need it. And Cockroach will try to do this as automatically as possible while going for variety. For instance, it won't put 3 things on the same rack because that would be dumb. You're trying to put them in different data centers. If you can't do that, you're at least going to choose different power distribution units, all of this stuff. And the configuration for that should be really easy, because when you start a Cockroach node, you will just basically give it a bunch of metadata, basically telling the node where it is. And then based on that information, it will be able to figure out where things should go, where things shouldn't go. And to talk between one another, there's a gossip network which basically transmits this information periodically, along with a lot of other stuff that they talk about to each other. Okay, so for instance, if I have this range A to I, and it's about 30 megabytes in size, which is great, but now people keep writing to this range because maybe there's something interesting that people store there. So it grows and grows and grows, and at some point it's 80 megabytes. So what's going to happen? Well, I mentioned that we're using a consensus protocol, which I won't get into detail in, but basically there's a leader of all of those yellow ranges. There's one guy who's in charge at any time, and that guy will just periodically look at the stats for the range, and he'll be like, well, this is kind of getting out of hand. This range is too big. And so then what he would do is run a distributed transaction, which updates the addressing for those ranges and basically just cuts it in half. So there will be a new line here, here, and here. The range which has gotten too big will just cut and split into 2 ranges, and then you have 2 ranges again which have acceptable size. Okay, and similarly, if 2 ranges are very small, then they will be merged. If one server goes down, then the remaining 2 guys will panic and be like, oh my god, we have to create a new range somewhere. They will find a new target server, tell that server, hey, take this range because we're in trouble. And then that server will just pull the range, again through distributed transactions, make it consistent so that there's no point in time in which there's actually any problem, and continue along. So this is kind of how Cockroach internally shuffles the data around, which means that you don't have to. Okay, so this is kind of the inner working, but but that, of course, doesn't explain how things get written there. Yeah, this is just basically the rundown for what I've said so far. Layered abstractions, I've talked about those. Distributed transactions, I will talk about a little bit more, but they're log-free, and the standard isolation that we have is serializable snapshot isolation. And if you just ignore the snapshot isolation, then it is exactly this serializable right here. The snapshot only comes from the fact that we are actually having a multi-version concurrency control system, so keys are stored with different versions. And of course, we use those to actually implement our transactions. But what you get is really serializable, and the snapshot isolation just tells you the implementation detail, basically. Okay? And on top of that, for a lot of common cases, we actually get linearizability. Whenever something is causally connected within Cockroach, so for instance, if the same client runs one transaction, and when it's done, it runs another one, that will also always happen in a linearizable fashion. So those two will never just magically have commit timestamps which point the other way. Okay, so a lot more could be said about this interplay between serializable, linearizable, spanner, and Cockroach, but maybe that's only interesting for some people, and if you are interested in this, then just come talk to me. Yeah, for the consensus protocol, which is having everyone that owns a piece of data agree on what's being written to it, we're using Raft. Just a few words about Raft. Raft is, you could say it's the successor to Paxos, because Paxos is pretty difficult. Raft was just handed in the Stanford PhD thesis in August, I think, but people wrote implementations of it way before. Unfortunately, they're all either broken or weren't implemented performantly enough, because we actually have millions of those ranges, millions of those colored rectangles, and we have maybe hundreds or 1,000 machines. And if we have one Raft consensus group that doesn't know about the others for each of those ranges, then we have millions of those groups, and they have to send millions of heartbeats, and that's too much. So we have to optimize the amount of network traffic, so we needed a special implementation for that alone, but also the Go Raft implementation that everyone was using was just broken, because in the face of network partitions, it went bust, so we're not using that. And we're working together with CoreOS on this, who are the guys who wrote etcd, and I think some were was not here, but the last meetup in Startplatz, which had their CEO, Brandon Phillips, give a speech. Okay. Okay, so maybe the one interesting technical thing that I can talk about is actually how are we implementing transactions. Of course, I cannot go into all the things that happen if transactions clash and the different ways to resolve this, but very simply, if you run a transaction, what is Cockroach actually going to do? So, as everything, it's a variation of two-phase commit. You can really do less phases, but at least we're not doing more than two. So, let's say you run a transaction, and so the first thing that happens is you write your transaction, or your transaction coordinator, which runs within the cluster, will write a transaction record. And it's not really written that way, but let's just assume this guy writes to this key. We have a key value store, and a way to store things is to pick a key and put some data there. And he writes to some internal key with your transaction ID, which in this case is 1, because you're probably the first guy running a transaction here. And he writes the status, timestamp, and priority. And initially, of course, the status will be pending, because your transaction is going to be running. Your timestamp will actually be, and timestamp is a misnomer, it's actually a logical clock. So we're using one that looks a lot like a Unix wall time, but it's actually a logical clock. So it's something like a vector clock. And it has a priority, which we won't talk about for now, because we're not talking about what happens if transactions clash. Okay, but it writes those two things into this internal table. And so now if you know the transaction ID, then you can actually go to that table and find out about this transaction. And this is a single source of truth. And because we have a consistent database, there's no such thing as getting out-of-date information or anything. If you read this value and you act upon it immediately within the same kind of compare and set, then you are reading the correct thing. So this is a single source of truth. And on this part, basically all the collision control is done. Okay? So now assuming my transaction started, it has written this value, then, well, usually you want to read something and write something in transaction. So if you read something, nothing really happens. You just read the values. and now you write something. That's going to be more interesting. So if you write something, say to key 1, we have an MVCC system, a multi-version system. So maybe there are some things written here. Maybe timestamp 1 has a value x, timestamp 2 has a value y, and now you're trying to write there. So what you are going to do is you're writing timestamp, I'm calling this timestamp t, so you're writing your transaction timestamp, and you're writing, well, whatever you want to write, let's say q, but as an intent. And this intent will basically point to your transaction ID, which will then, again, point to the transaction table. So if you write a value, you don't actually write that value so that everyone else will see it, but you write it as an intent. So other people may read it, but they will see it as an intent, and they now know a transaction has written to that value, and they can go to the transaction table if they suspect that you two might be doing something that's not compatible and act on this. So something that could happen is that another transaction that needs to write here will abort you, which means they update this entry, and you will at some point read it and say, oh shit, I've been aborted, now I have to do something. Usually you restart. Or a transaction could see that you wrote here and it's like, oh yeah, I do want to do something similar, but it's okay if I change your timestamp. So what it could do is increase the timestamp that I have written here for my transaction. So those are basically all the things that can happen. Okay, so this is all that can happen if two transactions collide. Either one aborts the other, or it pushes the timestamp of the other transaction, or it aborts itself, depending on priorities. Okay, so that doesn't sound so complicated. In the case that nothing went wrong, then I have written this value, maybe I've done some other stuff in this transaction number 1, and now I want to commit this. So I say, hey, I want to commit. And what does your transaction coordinator do? Well, it will go to its transaction entry, and if you haven't been aborted or anything that the transaction doesn't want to happen before it commits, it will commit it. It will set a new status, write this. Everyone else who reads this value after you will know it's committed. And now you still have those intents. So you don't actually have to resolve those intents. You can just return control to the client right away. You don't have to go around and poke at every value that you ever wrote before you go back to the client. You can do it right away. Why is that? Well, now if someone else comes along and they will see this intent, they will see the transaction ID, they will go to the table, they will know you're done, and then they will just change this value to an honest value. So what a transaction coordinator does when you commit is it actually commits, returns to the client, and then it's like, well, yeah, I should clean this up. So it will go there and do it itself. Okay, so after you return to the client, the server can burn, you don't care, it will be cleaned up. So this...
Sorry, what happens with the transaction coordinator dies?
No, the transaction coordinator is a cockroach node. So either it dies before the transaction commits, then the transaction has not been committed because it's not written there. Is it already answering your question?
Back to the client and said, okay.
No, it went back to the client. Okay, let's assume exactly this happened. So I've written 500 values. They're all intents. I'm writing committed, and I'm returned to the client, and then I die because someone drops a bomb on me. Well, then those intents are still there. The transaction is there as committed, so you know. Could be bad, but now everyone else who sees this will just know we're committed, so they will go there. So it's nice that basically you try to clean up after yourself, but it doesn't matter. You don't have to do it. It's the best effort. Yes?
In theory, you can't ensure progress with transactions. So you can have a transaction that starts, then another transaction that's running concurrently, and they can more or less abort each other all the time.
There's always one transaction aborts the other. They never mutually abort. That's why there's a priority. And yes, but
if you have like one needs to update row A and the other A and B, and does it in this order, and the other does BA, they can... So what... Yeah, sure. Yeah, it's hard, but what we do is that if a transaction clashes with another transaction, they will respect their priorities, and if they have, say, the same priorities, there's some randomized reshuffling. And in some cases, there's also randomized backoff. So this is something that really needs to be fine-tuned on large-scale deployments because, yeah, you are right. In theory, those things could kind of circle, and that should not happen. There's obviously, there's also a max transaction restart. So usually, restarts with Cockroach, they're very much expected because we're doing optimistic concurrency control. And the client usually will not know about them. I mean, because they don't care. They want to be committed or not. And if there's too many restarts, it will actually fail back to the client. So if that is an issue, then, yeah, if there's some kind of dead race, then there's something that we haven't done right here. Yeah, but this is definitely something that we have to get absolutely right.
Okay, but it doesn't sound outrageously complicated. It sounds usually fairly lightweight. Sure, you have to make sure that you don't run into any kinds of deadlocks that really degrade performance. But yeah, when I read this, I thought this sounds too simple to be like, why hasn't someone else done this? And in fact, this is not something that we came up with, but this is in a bunch of papers on optimistic currency control. And well, we're doing slight variations on them, but really this stuff is there. It's not that like we came up with it. And I think it's quite beautiful. It's part of what I like most about Cockroach. Okay, so I said serializable snapshot is the standard one, and this is really, well, now it's gone, but really this serializable here. We also offer another isolation that I think is very common, which is snapshot isolation. And in snapshot isolation, it's kind of close to serializable, but it does have some anomalies. But why we offer this is, well, there might be a situation in which you actually have a lot of transactions and it causes contention. So maybe serializable does restart too often, because those things will restart if someone pushes their timestamp. Remember, I had this entry in the transaction table with the commit timestamp that I want for myself. And if someone else goes in and pushes that timestamp because they found something that's newer, or I push it myself, then an SSI transaction will have to restart. And maybe that's happening too often in some special cases where we're really hammering on a set of values with a lot of concurrency. In this case, you might want to try snapshot isolation. Yeah, snapshot isolation has a few less restarts, but it does have bright skew, which is an anomaly that is bad for constraints and stuff like this. I'm not sure if I should go through this example, but who's interested in seeing an example of bright skew?
Yeah, why not?
Why not? Okay, at least one person. Okay, so with right skew, basically what happens is that each transaction sees the values that were there at the point when the transaction started, no matter what another transaction does concurrently. So I have a very simple example here, and I didn't write it, but I think, come again?
This is the I in asset, right? You only see what you...
Yeah, but the I in our asset is actually serializable snapshot, but this is a possible I in asset. Because this is snapshot isolation, but in Cockroach, most of the time you use serializable snapshot isolation. But yeah, this looks like it's cool, but it does have an anomaly, and this is this one. Okay, so think of this as banking. So we have two transactions, and they're basically doing the same. Let's say this one reads your two accounts, A and B. It checks if you have more than 100 euros, and then it subtracts 100 euros from your first account and commits. The second transaction does the same, but it subtracts from your other account. So it's basically checking out from two different accounts. And it never gives you any money, but it's how banks work. So if we run this with snapshot isolation, assuming you have 50 euros on each of your two accounts, lucky you, let's see how those two things run. And time goes from here to here. So my two transactions start. The first one reads A and B, reads 50, 50. Second one reads A and B, 50, 50. There's actually a lot of different orders in which this could happen, but the result is always the same. So now you're checking if you have 100 euros for the first one. It says, OK, so you just subtract 100 euros from this account. You end up with minus 50. That you write. And then you commit. No, and then you don't commit. Then this guy here does its check, but it does the check on the old A and B, which is 50 and 50. So it's like, hey, I still have money. Let's subtract 100 euros. And now you have minus 50 on your second account, and you commit. And all of this would go through with snapshot isolation because everyone had their own snapshot of the data. But now you have minus 50 euros, and the bank is sad because now you've overdrawn. So for you, it's great, but yeah. So this is something that can happen. So basically, that means constraints can break. And there's a couple other things that happen, but they're all variations of this. You're allowed to read data which is updated in a concurrent transaction that you don't see, but you make decisions based on what you think you see, but it's maybe being changed at the same time. So it's kind of semi-subtle, but yeah, this is something that can happen with serializable, with snapshot isolation. Often you're doing stuff where this cannot possibly happen, and then if performance is an issue, you might want to do this. But yeah, our default is serializable. Now maybe if someone's still interested in the transaction implementation internals, there's one thing I can say. Well, what would happen if we ran this in Cockroach with snapshot, with serializable snapshot isolation? Surely some point there has to be something that goes wrong, something that prevents something from commit, because this is not serializable. Because if you run this one after another, you don't overdraw. Okay, so that gives me a chance to talk about one thing that's being done in Cockroach to actually have this kind of behavior. It's kind of ad hoc, but hopefully it's interesting. So with a serializable transaction, there's actually something that's called a read cache in CockroachDB. And that's basically just a list, or obviously a cache of timestamps, logical timestamps, when a value was last read. So that value is used to figure out if someone, if you're reading a value that has been, no, wait. So yeah, this timestamp cache is used when you write to a value. And then if that value was read after you're trying to write to it, then you will get the updated timestamp. So it sounds confusing, but in this example, so there's two reads here. So the read timestamp cache for A and B gets touched here with the timestamp of this transaction. Remember, when this transaction starts, it chooses its timestamp. The timestamp that it will commit at is actually the timestamp that it starts at. It's kind of confusing, but that's what happens here. Then it reads those two values with this timestamp. So A and B will have the read timestamp cache equal to this transaction's timestamp. No biggie. We can handle this. So now the other transaction comes and reads. And it cannot have the same timestamp because you're using a logical clock. There's no such thing as two events happening at exactly the same time. So there will be a different timestamp here, and it will be a higher one. Or we flip the two. So assuming this is a higher one. So now it will read A and B again. So now the timestamp of A and B will actually be set to this guy's timestamp, which is bigger than this guy's timestamp. So this guy does his check, everything's still fine, things are going on. Now you're trying to write to A, but now this write will actually hit the read timestamp cache, which has been upped here, and will go back to this transaction saying, okay, I wrote your data, but actually I wrote it with a timestamp that's higher than what you wanted. And if those transactions are serializable, they will not want that. They will not want to commit with a higher timestamp, and so they will have to restart. So this one would back out here. This one down here wouldn't even know anything has happened, would just finish. And by the time this guy has restarted, probably this guy's already done, and so they'll just go. Okay? And then write conflicts, of course, are more difficult, and then one guy will have to restart. But yeah, I hope this was kind of accessible, because I've thought about this so much that sometimes it gets hard breaking it down to simple terms. Oh, we're on time. Do we still want to do this? So I could talk about temporal reverse, which is something that happens when you fail to be linearizable. I think I'm going to skip this slide. If you're interested in the subtle difference, you can always ask about it, and I'll probably just also send up the slide deck so you can look at it. Basically, usually we're linearizable even with Cockroach, which means that we retain the order of things that happen in absolute time, also in terms of their commit timestamps. So if two transactions happen in an absolute order, then their commit timestamps will also reflect that order. If you have things happen one after another in the real world, but Cockroach has no way of knowing this because you're not doing it from the same client, you're just triggering something outside of any known channel, then this might happen. My feeling, this is completely an academical interest, but something we can talk about. And maybe just to highlight why Spanner doesn't have this problem. They get linearizability. Spanner uses a very accurate time signal to do everything, and this is why they get linearizability all the time. But a very interesting fact about Spanner is that they always wait. So whenever you do a transaction in Spanner, it will wait for how much ever the clock uncertainty is. So they have a true time, which is basically something that measures very accurately the maximum clock offset between two nodes in the system based on all this GPS and atomic clock stuff. And they usually have between 1 and 7 milliseconds, which is pretty insane, given that normal NTP gives you like 150 milliseconds. So they really, really put a lot of energy into this. And with this 1 and 7 milliseconds, they actually have to wait it every time. So if you run a transaction, Spanner will do the transaction, then we're like, OK, you can go. And what that does is basically any other clock that's a little bit off from our clock will have proceeded while we wait. And so the commit timestamps will sort. And it's pretty crazy. And then this kind of leads to a nice anecdote on the next slide, and don't worry, it's about to be the last. So Spencer Kimball, the guy who invented CockroachDB, he actually he banged his head against the wall because he thought, well, it looks like they're doing all this atomic clock stuff just to deal with this temporal reverse, but no one actually cares about temporal reverse. So why are they doing this? And eventually gave up, and he just asked one of the guys, and they laughed. Because the real reason why you always have to wait this out is because if you are writing a value, then something that definitely needs to be true if you want to be consistent is that anyone who reads this value in absolute time after you have written it, they need to see it. And something that can happen is that the node that writes the value is slightly in the future, so that when you read it, it's still in the future, and then so maybe you don't read it. Okay, so this is something weird that can happen. And in Cockroach, because we don't wait on writes, we have something to deal with this. Basically, it means that if we read a value within a transaction and there's another value ahead in the future, which is weird anyways, but if we find one of those within the clock uncertainty interval, then we have to restart. Little fun fact, maybe not happening often in reality, we hope. As clock uncertainty goes down, maybe AWS will actually start installing atomic clocks in their data centers, because with the economy of scale, they can actually do stuff like this. Hopefully coming the next years. If that happens, then Cockroach will just be able to piggyback on this, and we can actually do the commit wait just like Spanner does, and then you will get basically the same thing. Get fully linearizable all the time. Now you get it whenever you're doing something in a causally connected way, in case you want that. Okay, summary, you're almost done. Just get my main talking points down. Cockroach, definitely inspired by Spanner, piggybacking on some of the things it's done. Also doing some things the same way, but definitely not all of them. Simple deploy, minimal configuration, both things that are not true for Spanner. And also internally, we're doing things very differently. Spanner actually logs everything, and we don't have this. So really think if we manage to actually build this system into something that everyone can use comfortably because it's done, then there's really no need to settle for low consistency except in specialized cases where you really need high throughput. Like Cockroach will never get even close to what you can write into Cassandra. That's just not possible because you always need to write to a majority. But really transactions can be fairly fast, and your database can be consistent and partition tolerant and still pretty available. So we're hoping that this is something that is going to be interesting for a lot of people. And in fact, some fairly big guys in the US, which Spencer has given talks to, were pretty interested. Especially Tumblr, who at the moment runs a 500-node MySQL cluster. So they're pretty. So and last word of advice, I think this is a really interesting part of Circle of Ideas. CP, consistent and partition tolerant, is really hard. It's easy to get it wrong. If you click this link, then you'll see a guy who basically tested a bunch of systems, and they basically all just went to shreds because they failed to do CP correctly. A lot of times because they relied on a faulty Raft protocol. And for us, really want to be open source because we really think the only way to get this absolutely right is if the whole world watches. There is FoundationDB, which is kind of doing the same goals, but they're completely closed source, and I will not trust anything that is not open to anyone's scrutiny. Did you have a question?
Yes, but when you're done. They
also
claim they survived the Jepsen test.
Foundation?
Yeah.
I have to check that.
At least a while ago. Yeah.
Okay. I remember there was only one database. I don't remember which one, but they claimed they had passed they had run Jepsen against their own product, but then it came out that actually they've just played with the timeout so that the leader re-election would be good enough to prevent inconsistencies. But I will Google that. I didn't know FoundationDB actually ran it.
At least they claimed it. Yeah.
They claimed it, okay. Well, if they didn't make it public, then I'm not going to buy it. Okay, so you are done. Thank you very much. If you need any of the links to get in touch, they're all there. Design documents, actually a fun read if you're into that sort of thing. Pretty approachable, I'd say, because I managed to read it, so that's got to tell you something. Cool, thank you. And questions, welcome. Can also just relax for a while and do the questions while we're standing with the beverage. Okay, thank you.
One question.
Yeah, go for it.
Who's responsible for maintaining the metadata for the branch of the table?
That's interesting. So you're asking about how someone will know where the data actually is stored? Yes, that's very interesting. So, okay, people are looking at me, so maybe someone else cares except for you. So this kind of using the key value store. So there's a special key range, which I think it's actually something like the 0 byte, 0 byte, 0 byte, meta 1, and then there's a range key. So let's say A, B, C. Whenever you want to have, there's one thing that everyone needs to know. All of the Cockroach nodes need to know, and that is kind of the sentinel range. So that is one special range that actually holds those special key ranges. Other than that, it's just a normal range, but it's basically just the first range by ordering. So this is also a normal replicated range. And if anyone needs to know where a certain key is, on which kind of range, then it would go to this range, form the key that sorts in the right place. So if I want the key ABCD, I would go and look for \0, \0, meta 1, and then this key. Then I would do a scan, because it's an ordered key value score, I can scan. So we'll get one entry, the next entry, and that will be an entry to a meta 2. With meta 2, I do the same thing, and then I get the actual replica set. We're doing 2 abstractions here because we want to scale to 4 exa whatevers. And if you address everything directly, it wouldn't scale. It wouldn't fit on a single range. So I have 2 levels of abstraction. And now you could say, well, this kind of sucks because this guy is going to be a hotspot. But in fact, you are going to cache those things super aggressively, and you will just risk addressing something to the wrong range, because then the range will just tell you, and you can actually look it up. And since the ranges are fairly long-lived, they don't move around in lightning speed. This is probably going to be fine. We have some simulations which make this look very much okay. Did that sort of answer your question? Yes, everything's replicated. So this guy is going to be on 3 replicas or more, usually 3.
So how do you execute a write? So client needs to connect to the leader?
No, the client directly doesn't. Of course, it's beneficial for the client to directly talk to the leader, and that's something we might do to improve performance. But basically, as a client, you connect anywhere. It doesn't matter who this guy is.
But you're getting redirected more.
Yes.
To the reader,
Yeah, you have to talk to the reader. Yeah, and so I think what we're going to do is, if you're connecting somewhere and we kind of know where you're going, then we will do it for you. But in the response, we'll actually tell you, maybe this guy is who you want to talk to.
Mm-hmm. And then the write is carried out on the leader plus sent to the other nodes?
So technically it goes into a Raft queue. Mm-hmm. So Raft you can think of it as a black box which does the consensus stuff. So the leader will try to commit this one entry after another, which means sending it through Raft to a majority of the nodes which acknowledge that they have it. So basically just Raft. And then once that's done, it's sent as committed. And there's some more fine-grained locking which we do. It's not actual locking, but it's more waiting. So operations which come into the Raft queue, which we know cannot be processed yet because they need something to be committed for, they will have to wait. And this is all done by actually locking only on those sub-ranges. So there's some sort of rearranging that goes on before you actually hit Raft, so that Raft actually has to just churn things through as fast as it can.
How would you ensure that you don't read an outdated value on some, let's say you write to node A, and it gets replicated to B and C instantly on the commit, and it gets eventually replicated to, let's say, D and E?
No, it's not eventually. There's no eventual replication. Things are replicated or not. So
okay, so it's
yeah.
Before it returns the commit.
Yeah. You actually that's a consensus latency. You can't just do best effort. You actually have to have it written. Yeah. So this is the one price that you really pay to be consistent. Always, you have to get it to a majority, unless there's some other magic thing that you can do.
Acknowledged to a majority.
Yeah. And there's actually a really cool animation about Raft where you can actually play around with it. I mean, if someone wants to see it, I'm happy to show it after we finish the questions. It's very interesting. Yeah?
Okay, so you've been, your disk has all been labeled SSD.
Uh-huh.
SSD is expensive storage, so have you done tests with normal?
No, we'll completely outsource this part. This is something that RocksDB does, the project run by Facebook. I think they're really banking on SSDs for write performance. Maybe they've written something about something else, but as far as Cockroach is concerned, RocksDB is really built to hammer in data at a great rate, but CockroachDB actually always has this consensus latency. Mm-hmm. So I don't think we're actually getting to the boundary of what RocksDB is designed for. What that could mean is that maybe SSDs will just be fast enough because we're not.
Well, you can, of course, you can cache use the SSD as a
Yeah. I mean, that's kind of what happens. So RocksDB fortunately is very, very tunable. So you can basically tune the write and read amplification, all those things. So you should be able to tune it to different sorts of underlying storages. And also, of course, it tries to be pretty smart about keeping the things that you actually want to access most of the time in RAM. I mean, it doesn't write everything down, obviously, it's an LSM. But yeah, I'm not sure how far we want to go in Cockroach with basically providing images or providing configurations that actually go deep into RocksDB, because that would definitely mean building your own. Since it's an open source project, I mean, go ahead. You can basically change everything in RocksDB. You can completely rip out RocksDB and put something else in. But yeah, I think RocksDB has SSDs in mind, and hopefully those eventually won't be as expensive anymore, but sure, to write huge amounts of data, it's still going to cost money.
Well, you know, they are, yeah, if you have huge amounts of data, it's always going to be
Yeah, I mean,
because just the lifetime is not so.
Yeah. But then at the very least with RocksDB, you're able to fine-tune the write amplification. So if you tune that to be fairly low, then you're actually not killing your SSD as fast as otherwise. I mean, you're always killing it. I mean, it happens. Yeah, in some cases when maybe your write performance is not the most important thing in the world, I mean, technically it will just work with a standard HDD. It may not be as fast.
Yeah,
but it's really hard to see where the bottleneck's going to be.
The same thing would be like just to see how your stuff behaves when the when the write latency just goes up in order of magnitude.
That's true. Yeah, I mean, it will get slower. It just propagates.
Yeah, but how much slower? Does it go as linear?
Yeah, we're definitely psyched to actually have a beta out, because then we can actually test those things. Yeah, we're fairly close, but we're still working on the internals. So we have internally like clusters running and everything, but the outside world thing.
There's a lot of append writes, so basically you have multiple sequential streams to write to, and that's not the baddest thing you can do, or the worst thing you can do with spinning. Yeah,
right. You're always writing continuous streams, more or less. You don't have random seeks most of the time. You're always reading whole runs. Yeah, so I figure it shouldn't be that bad, but I'm really not an expert on the RocksDB or the storage layer.
Do you have anything in place to kill a node if you detect degraded network or latency or stuff like that? Because if you write to 3 different data centers and suddenly the latency goes up plus 50 or more milliseconds between a link, then you kill performance for all your writes.
Right. So what we definitely want to do is one critical one is the range leader, right? The range leader shouldn't be on a broken machine that has network loss. That's just something we'll add on later. I mean, it's not important for the core design, but yeah, we'll definitely have checks that if a machine suspects that it's not the guy who should be in charge, also because of the latency to others, it would just kind of abandon.
Because lots of the problems is not necessarily you cannot talk at all to
phone,
but you have packet loss or latency goes up or
or your messages go one way but not the other.
Then here you reach the node.
Yeah, and for that I have good news. Like we definitely want to spend a substantial amount of our time actually checking those things. So just today I looked at NetDM images in Docker, with which you can actually do all sorts of random packet reordering, package dropping. It should be a lot of fun, and yeah, we kind of want to do the Jepson thing all day long. Yes?
What kind of application would be the ideal client for this database?
Well, anyone who doesn't just write data all day and never needs it again. So basically, what I would have in mind is someone who has data which, they would be storing it on Postgres, but they just can't because it's too huge. So that would be the basic thing, because we are going to be semi-relational. Also, anyone who would want a key value store. Basically, anyone who can live with the replication, the consensus lag. So really the only thing that I think is a killer for Cockroach is if you actually want to just push in massive amounts of data and you do not have the patience to wait until it's replicated. Maybe you don't even care about it being replicated, you just want it to go in. If you drop a little bit, I don't care. So if you're thinking of a log stash, for instance, and maybe you don't want to put all your logs in 3 different databases, maybe you just want to dump it into Dynamo or Cassandra or any of those.
Is it suitable for multiple data centers?
Yeah, that's especially what it's supposed to be done for.
There is no particular algorithm to distribute these
ranges?
These ranges through data centers.
No, I mean.
Is it possible that, for example, most of my data in one data center locally to my client. But
Okay.
But some 10% or something is missing and is are on remote.
I mean, so you're basically talking about being able to manually control which things go where. Well, you know, it's something that we haven't built yet simply because we think we should be adding the bells and whistles last, but that's something that can be done.
It's complicated.
Well, you just need to make sure.
Theoretically, you can imagine that.
Yeah, but
Majority
when
is
you get
local.
to the details,
Yeah, I mean,
you get broken.
yeah, do you have an example? That's interesting.
Definitely.
What's the kind of thing that goes wrong?
In terms of Cassandra, for example, if you think of, let's say, videos is not a good thing to store in a database, but if you think you want to store YouTube videos for the Germans in Germany, for the US people in the US, you want to distribute the videos depending on, let's say, hit counters or something like that.
Okay.
You want to move them.
Oh, yeah, yeah.
You get into problems when you want to replicate the data or repair nodes or something like that, and that's the complicated part in it. It's a valid idea to do that, but it gets complicated when you can come to beta and into the implementation.
Yeah, so I don't think we'll have like sophisticated algorithms that allow you to do complicated things like this, but what you can do is kind of influence, maybe at some point influence which ranges get preferred locations simply by maybe assigning a weight to two different key ranges. I mean, we have a zone-based configuration model, which means that basically you have different configurations for different contiguous key ranges. So if everything that you want to have in Germany has a prefix Germany, then Cockroach could certainly use this to give higher priority to those things when they are actually moving. So give higher priority to those things that they will tend to move to Germany. But I don't think we're going to have something that actually allows you to just like kind of swipe data around and make sure it sits exactly where you want it to be.
But if the data are randomly distributed, then the fastest transaction is limited by delays between.
Yeah, but yeah, that's correct. Yeah, if you put one data center in Singapore and the other one in, let's say, Frankfurt, and maybe the other one in, well, what else is not in, yeah, Sydney, then you will always pay the lag between, well, from one point getting to two of the others. Yeah, this is something definitely that you have to live with. But you could, of course, do, yeah, I mean, you could do more data centers. You could do 3 data centers in Frankfurt and then 1 in Singapore and 1 in Sydney. Then you would mostly just use those 3, and those other 2 would, you know, just kind of be there and slow everything down. You could do that, but
other data centers, even without majority, will have.
No, data center doesn't have to do anything with majority. The majority can be anywhere. It just means that each piece of data is, well, say on 3 replicas. It has to be on 3 replicas, but it doesn't specify where those replicas have to be. But natively, I think Cockroach will try to get as much variety in as possible, because if you have things in the same data center, then they simultaneously fail, and you usually don't want that. So Cockroach would try to move them outside, but you could think of devising mechanisms or come up with situations where you would want to cluster some of the replicas for performance. But you know, right now we're at a stage where really I don't think we actually think about this much. But I also do think that we have configuration possibilities in place that allow for some of this, but certainly not all, because as Robert said, it probably gets really confusing at some point.
Some extension to this question is if you're thinking rows instead of key value, the overhead explodes if you have very distributed values in a row, or is it?
Yeah, you definitely don't want spare tables. No, you actually want to store actual data in there.
No,
because
SQL
huh?
No SQL on
No, don't do it, please. no, don't emulate Bigtable on Cockroach.
Yeah.
No, yeah. So, of course, internally we map database, table, and then primary key to a string, and then inside of that we use a protobuf that encodes the rest.
You have to look around.
Yeah, but it's a protobuf, so it will skip empty fields. So you might be able to do something, yeah, but maybe don't.
Yeah.
Okay.
Now you mentioned FoundationDB as a commercial alternative.
I'm not sure it's an alternative, but it actually exists and they have it, and we're still building it. So
it has similar goals as I
yes.
Yes. I remember a colleague of me was evaluating FoundationDB for his project and finally had to discard it. It doesn't support a schema update on the fly.
Haha.
So I understand CockroachDB is primarily a key value store, but you mentioned adding
Yeah, this definitely belongs to the aspirational SQL field. We've all read the schema change paper by Google, and we all said, hey, we want to do this. So obviously, this is like a big thing, but we really do want to try. But given that we're at the key value store, there's a long way to go. What we do, however, is we intentionally haven't come up with some sort of API for the structured data, which is what is just below SQL, because we want to make sure that we actually make it powerful enough to actually be able to deal with schema changes. So we'll be thinking about online schema change a lot when we build the structured data API, but even from there, it's still something to do. But yeah, it would be absolutely the absolute dream to get rid of migrations. If you have this, I think everyone will just use you because just for convenience. Yeah.
Have you done any comparison to other databases, Postgres or?
No, it's happening as soon as beta comes out. We'll be actually tuning for performance. Right now, it's get everything completely right. Don't.
So you have no clue now.
No, we have no clue. I mean, we know we've benchmarked, simulated some individual pieces. For instance, the gossip network, which is not that crucial for performance. It's more of a showstopper. If the gossip network is too complicated, then it's doomed. We've also run simulations on transaction restarts and how many you get if you have contention. But that's a simulation, and simulation is a good thing to convince yourself. But really, you want real-world testing. And yeah, we're going to be doing a lot of this. So Cockroach, very young project. I think the first commit was in February, and there's no one full-time on it. I mean, right now there is, but yeah, you can picture that right now we're just pushing for something that we can actually use to get a bunch of money to actually do much more work. So this is kind of where we're at.
What language is it written in?
Go. Okay. Yeah, everyone's from Google. And actually, fun fact is Spencer, who, again, the benevolent dictator. Well, actually not even dictator. No, I like this term because I read a discussion about Docker from one of the guys at CoreOS, because Docker is now adding kind of competing features to manage clusters and kind of moving out of its original scope. And then in that context, someone called the guy who runs Docker a benevolent dictator. And I like that. So I'm using this for Spencer, but he's really not a dictator. But what was I going to say? Question? What was the question? Completely lost.
Language was the thing.
Oh, yeah. Yes. Spencer, so the guy who wrote most of the code, actually started writing Go on that project. So. But yeah, I think it's a very good language to write such a project in with a finite scope and with you in a place where you want quick onboarding of people, because anyone can really just open it and they will kind of understand it. There's no pages and pages of abstractions. The tooling is good, so it's by design. It's not the language that I think is the most beautiful in the world, but it really does a damn good job of working in everyday life. And yeah, good choice.
Do you already have performance instrumentation?
No.
No, that's too bad.
Will come,
Any
eventually.
plans for that?
Yeah, I mean, we're really pushing beta out, and then we have plans. The thing is, we have plans for everything, but we have full day jobs. But what would you want to see? Yeah. Well, I think we'll just hope that someone else has done something similar and then probably incorporate it. Yeah. I think we have something, someone put something in there at some point, but I really don't remember now.
If you come out with the beta, what kind of API do you think you will have for storing the data? Is it HTTP based or is it protobuf over?
Yeah, I mean, eventually we'll have different ones, but for now I think we're going with HTTP, simply because it's people can play around with it.
Makes sense.
Internally, of course, because all of the nodes have to handle transactions. Internally, they already have a full implementation of a client. So it will be very easy for us to actually have a client which is in Go. And since we're using protobus, hopefully we can get other clients fairly quickly, because the external clients don't actually have to do a lot of the work. But yeah, ideally everything from just running transactions on the fly. We actually don't buffer transactions. They run immediately. Spanner buffers them. To prepare statements, stuff like this. But for now, key value.
Apropos clients, where the listeners are, does every node have a listener, or is it only one listener for the whole cluster?
What do you mean by listener?
Listener, where the requests
Oh, well, every node will serve clients. So actually, the nodes listen on different ports for other nodes, which is the gossip network. It's kind of internal. And then they will also export the Cockroach API. Because, I mean, if you don't want that, simply don't open that port.
every node?
Every node, yeah. This is a good thing. The system is completely homogeneous. You run the same binary everywhere with, configs adapted to the host, of course, but also very minimal command line configs. And they will export the exact same Cockroach database to everyone. So it should be fairly straightforward. Okay. Everyone exhausted? So, you have another one? Go for it.
Will there be a manager node? Or
No, completely homogeneous. No manager. Because that would suck, because you would have to manage the manager.
And exclude nodes on the fly?
Yeah, so this is all stuff that we haven't really done yet, but there, of course, we have a root user internally, and we have certain things that we want nodes to be able to do. At the heart of it is the range, which basically just manages itself. But of course, you can trigger those things, and it's fairly easy to provide access to this. But so what you can definitely do is shut down a node gracefully. That's definitely something we're going to have. Also, probably something that tells a node to get rid of all of its ranges before it shuts down, so that the transfer is even more graceful. This is all things we can do, but right now we have not devised an exact plan of what we can do from the outside. But we definitely want the system to be kind of self-contained and autonomous, but you also should be able to know what's going on. That's a lot of logging that we're going to do, log everything basically. And the other thing that we definitely want to do is give you kind of cracks in the system where you can actually trigger those things that usually it does on its own. Especially if we want online migrations. We'll have to have this.
How complicated is the bootstrapping process? Initiate the cluster.
Well, if I compile this thing and then I type make acceptance, then it will build a Docker image and fire up a cluster with 3 things, and then have them connect to each other, and then shuts it down. And that's the init is really just one. It's /cockroach -- bootstrap -- gossip, and then you give 2 other IP addresses for the other nodes because it needs to replicate, and then SSD equals, and then you give a bunch of folders where it puts the RocksDB instances, and then we don't even want to start with config files, so it should be that easy. At least for now. Probably at some point, when the reality hits, then we'll have to add some of this, but the average person shouldn't have to do anything else.
And then every node which will respond to gossip protocol will be accepted and...
I mean, the nodes have a cluster ID and they talk over SSL. But yeah, they will basically share the other nodes which are out there through the gossip protocol. So ideally, if you fire up a new node and it knows some entry point, it will automatically get the rest.
So theoretically, you can misconfigure some system.
What do you mean?
So like you put like a node accidentally and will join the cluster.
Oh yeah, sure, you can add one accidentally, sure. I mean, you can do everything by accident, right? You can accidentally paint a Picasso. I mean, could happen. Not likely, but yeah, I mean, you could, if you have some automatic deploys and you've messed something up, maybe you're going to add nodes to your system which shouldn't be there. But it's not that much of an issue unless they run on the FBI servers or something, I don't know, and you don't want them to know. Sure, but yeah, deploy should be easy, and you can do this by accident.
Who's going to need etcd when it's ready? So
etcd has kind of a different scope, but yeah.
Overlapping, I think.
Yeah, etcd is not made for this scale. So etcd is more of I think of it more as service discovery and config store. But yeah, it does kind of the same thing, except that it doesn't scale as well. Yeah, so some people, might not want to use etcd because of this. They've still been very friendly to us, and I think they can take the competition. Maybe also banking on just replacing etcd by CockroachDB at some point, I'm not sure.
Yeah, it would make sense because there are some issues with etcd and yeah.
Like what?
We had issues because we used it and it was a previous version and they dropped support for for older systems, they had we had seen a lot of these internal raft errors and stuff like that.
Oh, I see. Yeah. But that was the old. So I think back then they relied on GoRaft, which is the broken one, and they're actually investing a lot of energy into writing the new raft together with us. So hopefully this is not going to happen again. But yeah, it sucks.
And it was slow, by the way. But,
yeah. Hopefully not this one. Okay. Everyone satisfied? Cool. Then thank you again. And I'm going to get the tea.